All right, so today we're going to talk about second order passive filters. So since we're dealing specifically with voltage filters here, essentially all we're going to be dealing with is series RLC circuits, okay? And effectively, whichever element or whichever combination of elements that we choose to take the voltage drop across as our output will tell us what kind of filter we have. So when we looked at our first order filters on Monday, when we took the voltage drop across a capacitor, we had a low pass filter. When we took the voltage drop across an inductor, we had a high pass filter. And it was when we took the voltage drop across the resistor that we just got something different. That was the ones that were a little harder to figure out, okay? So we can definitely do second order high pass filters and low pass filters. Again, it's just a series RLC circuit where our high pass filter is going to involve taking the voltage drop across the inductor, and our low pass filter is going to involve taking the voltage drop across the capacitor. I'm going to give you guys those relationships in a couple of minutes, but because we've already seen those responses generally, I want to look at something else. So I want to look at either a band pass filter or a band stop filter with you guys. I think I'm going to look specifically at a band pass filter because I have an idea for a little design project that we could actually do in today's class meeting that'll be similar to the filter design projects I'm going to ask you to do that I think would be helpful. So let's look at the following circuit, okay? So here is our input signal, Vn, as a function of omega. And I'm going to put an inductor here, having an impedance of j omega L, and a capacitor here, having an impedance of 1 over j omega C. And then we're just going to take the voltage drop across this resistor as our output signal. Okay. So this will be V out as a function of omega. So I've already told you that this is going to be a bandpass filter, but let's see if we can just look at this thing and kind of infer why that behavior is going to exist, okay? So at incredibly low frequencies, what is our inductor going to look like? A short circuit, okay? And what's our capacitor going to look like? An open circuit. So essentially we have a short in series with an open. So that path of the resistor, excuse me, the inductor and the capacitor overall is just going to look like an open circuit. So no signal is going to get passed through at very low frequencies. Well, at very high frequencies, then our inductor is going to look like an open circuit and our capacitor is going to look like a short circuit. So we're once again going to see that no signal gets passed through to the output. It's only somewhere in the middle where effectively the reactance of the inductor and the reactance of the capacitor cancel each other out so that that whole path looks something close to a short circuit. That's where we're going to get our maximum value of our output voltage because all of our input signal gets passed along to that resistor. So with that in mind, let's investigate how this guy works more quantitatively, okay? So down here, because this is going to get a little big, I'm going to do just my basic transfer function h of omega using the voltage division rules, right? So I'm going to have, just to remind you, this is simply the ratio of V out over V in. And so I'm taking the voltage drop across my resistor, so I'll have an R in my numerator. And then I'm just going to have my total series resistance in my denominator. So I'm going to choose to write that as R plus j omega L plus 1 over j omega c. Okay. Now I've got a fraction in my denominator, and generally speaking, I hate that. So in order to get rid of that fraction, I'm going to multiply by, and this is where it might seem a little bit odd, instead of multiplying just by j omega c over j omega c, I'm going to multiply by negative j omega c over negative j omega c. Let me go to the right page on my notes here. Nope, I lied. I was looking at the wrong page of notes. I'm going to do positive j omega c over positive j omega c for this one. Sorry about that. Okay. So this is going to wind up giving me j omega rc in my numerator. And then in my denominator, I'm going to have an imaginary term. So let me just go ahead and put that plus j omega rc. For my real term, so let's play around with this math here just real quick over here, right? So essentially, I'm having j times omega c minus 1, excuse me, that should be an L. Omega L minus 1 over omega c is what this part right here can be rewritten as, right? Because we know that 1 over j is the same thing as negative j in the numerator. That's being multiplied through by a factor of j omega c. So j times j is going to look like a factor of negative 1. And so what this thing is going to come out looking like actually is going to be 1 minus omega squared LC. So from this particular form, I can do the exact same thing that I did every time I wanted to get my split it up into its real and imaginary parts like we did in our last class meeting. So I'm just going to take that expression, j omega RC divided by 1 minus omega squared LC plus j omega RC. And I'm going to multiply that by the complex conjugate of the denominator over the complex conjugate of the denominator. That's going to look like 1 minus omega squared LC minus j omega RC. Goodness, that should be a closing brace. Divided by that exact same quantity. And doing this math leaves me with omega RC quantity squared over 1 minus omega squared LC quantity squared plus omega RC quantity squared. So that's the real part of my result, plus j times omega RC times 1 minus omega squared LC all over that same denominator. So now that I have my transfer function broken down into its real and imaginary parts, I can simply square the real part, square the imaginary part, add them together, and take the square root of the whole thing to get my magnitude response, just like we did in class the other day. So the magnitude of h of j omega is going to be the square root of my real part squared plus my imaginary part squared like so. And let's do this out real quick here, right? So I'm gonna have omega RC to the fourth power plus omega RC squared times 1 minus omega squared LC quantity squared all over 1 minus omega squared LC quantity squared plus omega RC quantity squared, square that whole thing, okay? So I can pull a common factor of omega RC squared out of that numerator, right? So that would look like omega RC squared times 1 minus omega squared LC squared plus omega RC squared all over 1 minus omega squared LC squared plus omega RC squared, square that whole thing. And we can see that this term cancels out one of the powers in the denominator, again, like every other thing that we've done. And so our result is simply going to be omega RC divided by the square root of 1 minus omega squared LC squared plus omega RC squared, like so. So let's look at what happens when we're looking at H at 0, okay? So at 0, angular frequency of 0, our numerator looks like 0, and then we have 1 minus 0 plus 0. So that's just 0 over 1. So at very low frequencies, we have 0, okay? And then for high frequencies, we are going to have a numerator of infinity. So omega squared times LC is going to be much, much larger than 1. So we can just throw that thing away. So effectively, we're going to have infinity to the fourth power plus infinity squared, which is going to look like infinity to the fourth power, okay? Well, the square root of infinity to the fourth power is infinity squared. So essentially, we have infinity over infinity squared, and infinity squared is somehow much larger than infinity. So it also looks like 0. So at very low frequencies, we don't pass any signals. At very high frequencies, we don't pass any signals. So presumably, we're just passing the stuff in the middle, which is exactly what we would expect out of a band pass filter, okay? So for this guy, if you recall from the graphs and stuff that I drew on Monday, we're going to have a resonant or center frequency as well as a low frequency minus 3 dB cutoff and a higher frequency minus 3 dB cutoff, okay? So for our resonant frequency, well, we actually already know what that is. Well, because what's the resonant frequency of a series RLC circuit? Square root of 1 over LC. We talked about that when we were doing the transient analysis. This is literally nothing different than that, okay? So omega naught, that looks like a W, is just the square root of 1 over LC from our previous work, okay? Now, calculating omega low and omega high from this relationship is rather difficult to do by hand, okay? We still want this thing to wind up being equal to 1 over the square root of 2, but we're going to wind up having two different solutions. So when I solved it, I just did it symbolically in MathCAD, so I'm just going to give you the result, okay? So what we're going to find is that our low frequency cutoff is going to be at negative R over 2L plus the square root of R over 2L quantity squared plus 1 over LC. Now, before we move on to our high frequency cutoff, does that look familiar to you guys? So when we have a series RLC circuit, when we were doing our transient analysis stuff, what was alpha? It was R over 2L. And omega naught was the square root of 1 over LC. So this is literally just negative alpha plus the square root of alpha squared plus omega naught squared. Literally, S1 that we calculated in our transient stuff multiplied by a factor of -1. Okay. Omega high is positive R over 2L plus the square root of R over 2L squared plus 1 over LC, all of that underneath the square root. And again, it's just one of those natural frequencies for a series RLC circuit, except that it's now a positive frequency instead of a negative frequency. Okay. So these are our 3 dB cutoff frequencies on both the low side of omega naught and the high side of omega naught. So we could say from this that our bandwidth, for whatever it's worth, is omega high minus omega low. So I want you guys to do the terrifying amount of math here and figure out what that's going to be. So the big thing under the square roots wind up canceling each other out. So we just have R over 2L minus negative R over 2L is 2R over 2L, or just R over L. So essentially, for this simple second order bandpass filter, our bandwidth is only dependent on the value of the resistor and the value of the inductor. So if, I don't know, I gave you guys a design problem like this, if you assumed a value for the resistor and you knew what bandwidth you were aiming for, you should be able to find out what inductor gives you that bandwidth very easily. And then knowing that inductor value, you could now solve for the center frequency, omega naught, because you only have one other variable, C, to determine. So that should be an incredibly easy design project. I'm telling you that it should be an incredibly easy design project because it is astounding how many of you guys will come up and ask me questions about not knowing how to do it when it is literally just assume a value for R, solve for L, and then solve for C. And we're going to work an example where that's exactly what we're going to do. So there is no reason whatsoever for you to ask me a question about how to do this. I want to be clear. This should be the easiest design project you've ever had. Okay. The last thing that we need to sort out here is our phase response, okay? So theta as a function of j omega is, as it has always been, just going to be the inverse tangent of the imaginary part over the real part, right? Notice that both our imaginary and real parts have the same denominators, so we could ignore them. So we're going to have essentially omega RC times 1 minus omega squared LC divided by omega RC quantity squared. This guy cancels out one of those powers, and we're left with the inverse tangent of 1 minus omega squared LC divided by omega RC. Okay. So design example time. I am an old man. And so when I drive home, if I'm in a bad mood, I'm listening to my death metal and all of that kind of stuff off my phone. But when I'm in a good mood, I typically listen to the oldie station here in town, KPCH 99.3. Okay. So we're going to say that our center frequency for the bandpass filter that we're looking for is 99.3 megahertz, okay, which corresponds to that particular radio station. Now, does anybody have any idea of what the bandwidth of an FM radio station is? Do any of you guys listen to FM radio stations when you're driving to campus or anything like that? Or am I just that much older than you all that you don't even listen to the radio anymore? Seems like I might be that much older than you guys. Geez Louise, you're making me feel like shit. All right. So for what it's worth, the next time you actually, I don't know, get in your parents' car or something like that, and they listen to the radio, whenever you change the dial, it jumps up in 0.2 megahertz increments. So your stations are going to be like, I think they start at 88.1 megahertz and they go all the way up to 107.9 megahertz, and they are in 0.2 megahertz increments. So that means if our radio station, let me draw a shitty graph here. You guys don't have to pay attention to this at all. But if we're looking at the frequency spectrum here, right? So let's say that this is 99.3 megahertz. Corresponding to the station that I'm interested in. And over here would be 99.1 megahertz. And over here would be 99.5 megahertz. Well, each of those three frequencies is the center frequency for their respective station, okay? So that means that at most, the bandwidth of our individual signal could extend to right here, the halfway point on the left-hand side, and right here, the halfway point on the right-hand side, because if it was any wider than that, we would accidentally pick up 99.3 when we were trying to listen to 99.1 or 99.5, okay? So that means that this bandwidth in total ranges from 99.0 to 99 point, sorry, that should not be 0, that's 0.2, to 99.4. So this is 0.2 megahertz or 200 kilohertz. So that's our bandwidth, okay? That's the minimum possible, or actually that's the maximum bandwidth that these stations could have and not interfere with each other. Okay. So if we circle back around here, now I know that my bandwidth is, let's call it 0.2 megahertz. Both of these are in terms of linear frequency. All of our equations are putting everything in terms of angular frequency. So how do we go from linear frequency to angular frequency? Omega is equal to 2 pi f. Okay. So omega naught would just be 2 pi times f naught, which if I throw that into my calculator, 2 pi, oh goodness, times 99.3 times 10 to the 6th hertz is going to come out to be 623,920. So actually 623 million, excuse me, 920,000 301 radians per second. So let's call that 623, actually 624 megaradians per second, roughly. Okay. Our bandwidth in terms of frequency is just going to be that 0.2 megahertz times 2 pi. So 2 pi, goodness, times 0.2 times 10 to the 6th comes out to be 1256637.061 radians per second, or 1.257 megaradians per second. So if I choose to implement my filter with a resistor of R is equal to 1 kiloohm, then what does the value of my inductor and capacitor have to be? And here's where we're going to use those simple relationships, right? So we know that our bandwidth is equal to R over L. So that means L should just be R over our bandwidth in radians, right? So that is going to be, store that as Y. So 1,000 divided by what I have there gives me 0.00775 henries, or 795.775 millihenries. And we know, kind of running out of room here, that omega naught is equal to the square root of 1 over LC, right? So that means that omega naught squared is 1 over LC. And so if I'm algebraing this in my head correctly, C is going to be 1 over L times omega naught squared. So that's going to be 1 over my prior answer times what I have in my calculator as x squared. I must have algebraed something wrong, because that comes out to be 4.1 times 10 to the minus 27 farads, which is definitely not right. Yes, what did I do wrong?
Ask about the henries to millihenries, because wasn't that?
Oh, that should be micro.
Yeah, okay, is it micro?
Yeah. That seems like a ridiculously aggressively small thing, so I might have mathed this wrong. I genuinely don't think I did, though.
I got 2.044 times 10 to the negative 24.
That still seems super small. Let me just see something here real quick. Let me do that as A. Let me do that as B. So the square root of 1 over A times B. Yeah, I did something wrong somewhere. Maybe it was simply putting it in my calculator or something like that, because when I just did 1 over the square root of A times B, which is where I stored L and C respectively, I got 5.5 times 10 to the 14, which is definitely not the thing that we were looking for. So let me try to calculate this correctly this time, okay? So let me just double check that algebra. Omega naught squared is equal to 1 over LC. I think we should all be on board with that one pretty easily, because that's just squaring both sides. Yes.
Should your micro be 7,957? Because you did 10 to the fifth. Isn't micro 10 to the sixth?
Oh my goodness. Did I? No, I missed putting a 0 in.
Okay.
So thank you. You were correct, but I wrote it down wrong. Yeah.
I ended up getting 3.227 times 10 to the negative 15. Still a long
I mean, that's in the femtofarad range, so that's not out of the realm of possibility. You can buy femtofarad size capacitors and all of that kind of stuff. What did I fuck up here? Well, let me make sure I just have the right stuff stored in my calculator. I feel like it's user error on my part. Okay, so that is X. So that's fine. So
0.01.
So when I just put it in a moment ago, I got like literally just here a second ago, 3.228 times 10 to the minus 15 farads, which would be 3.228 femtofarads. And I believe that's what you got as well. So let's try that. That seems the most reasonable number that we've gotten thus far. I feel like a jackass for saying there's no way to screw up this easy ass design problem, and then I managed to screw it up at least twice here in the last couple of minutes. So that's what my hubris gets me. All right. So I just want to throw this into LT Spice real quick and just kind of see what shakes out, right? So I'm going to start with my voltage source. Let me get this dumb thing out of the way. So just to remind you guys, because I just came in with a pre-set up circuit the other day, I'm going to right click on this voltage source. I'm going to press the advanced tab. And the only parameter that I'm going to edit is this AC amplitude. Okay. And I'm just setting that AC amplitude as 1 so that my voltage source is effectively 1 angle 0 across all frequencies. Okay. Now I'm just going to set up my filter circuit. So I'm going to put my inductor up here. And I believe we said this was 700 something. Let's look. 795.775 microhenries. 795.775. And for what it's worth, I'm going to make sure that that series resistance is 0 so that I'm just dealing with a pure inductance. Shouldn't matter because we're using a 1K resistor. For my capacitor, I'm going to drop that guy over here. And this guy was 3.228 femtofarad. So that's going to be just lowercase f. And then over here, I have my 1 kilo ohm resistor, which I feel like I probably should have made a 10 kilo ohm resistor, and that capacitor wouldn't have been quite as small, but it'll be okay. I need to put ground down here somewhere because LT Spice requires us to have a ground. And I'm going to label the voltage drop across my resistor as V out. Like so. And now I'm going to run a simulation. So we need to do an AC analysis. I want to do a decade sweep. Once again, I'm going to start with just 1,000 points per decade because this seems to be what you students typically use. And I'm going to show you once again that it gives you garbage. And because I'm really only interested in what's going on around my center frequency, let's start this at, let's say, we're at 99.3. So let's start it at 95 megahertz and let's end it at 105 megahertz. So for what it's worth, if I did 95 capital M, LT Spice doesn't know the difference between capital M and lowercase m, so that would treat it like it was millihertz. So I need to do specifically MEG for megahertz here. And down here, I'm going to do 105 MEG like so. And hopefully this works correctly and I don't embarrass myself further, but you know, at the end of the day, it is what it is. So if I click here, so that looks reasonably okay. It looks way more kind of pointy than I would expect it to be just because of the number of data points I have for each individual decade here. Let me get this out of the way so we can see it, right? So 1,000 points per decade looks okay, but once again, I'm just going to edit this and do it as a million. And when I run it now, it actually looks a lot better. So let me go back and I want to show you something that's also important here that actually got missed. Okay. So if I put this guy back at 1,000 points per decade, right, which seems like it's a whole lot of points per decade, it looks like my peak value of my filter's output never actually gets up to 0 dB. What does 0 dB correspond to? Anybody know? So the dB is definitely for decibels. So 20 log of what is going to give me 0? 1. Okay. So 0 dB literally corresponds to my output voltage and my input voltage are the same thing. Okay. So if we looked at just this graph right here, we would erroneously infer that our output never actually gets all the way up to the value of our input signal, okay? That can happen for some filters, but we shouldn't expect it to happen on any of these simple first and second order filters. The peak value should always be a 1-to-1 ratio between input and output signal, okay? So we accidentally throw away a pretty considerable amount of information for this particular circuit by not having enough data points for each decade. When we get it back up to that 1 million, actually that would be 1 billion, which would still probably be fine. We now see that the curve looks much, much smoother and our output signal actually does hit the 0 dB that we would predict based on everything else here. So now let's just look at this guy and see where this center frequency hits, okay? So it looks like our center frequency is at 99.296 megahertz, so pretty darn close to 99.3. There's a little bit of, rounding error in our component sizes and all of that kind of good stuff. Let's see where we get when this guy falls down to negative 3 dB. So because, oops, I'm going the wrong direction. We have so many data points, I have to hold that arrow over for quite a while. So -3 dB or thereabouts is at 99.2 megahertz, which is what we should expect for our low frequency side. And then on the high frequency side, realistically, this should be at pretty darn close to 99.4. Yeah, so 99.402 and some change. So we, with a little bit of math hiccups here and there, managed to design a simple filter circuit to pick out one particular radio station that we were interested in. Now, could you put together an RLC circuit using these values and actually pick up that radio station? No. The reason being is that you need an antenna to actually receive it. You need a power amplifier because the value of your signal is going to be so small when it gets to us. Even from here in Ruston, it's going to be small, so we need to amplify it and do a couple other things. But the filtering side of our whole radio circuit would actually look like these particular components if we simplified it down to a series RLC network. Okay, so this is what our response curve looks like when we have what's called very high selectivity, meaning that we have a very narrow bandwidth. If we were allowed a much wider bandwidth, it would, that peak would be way more spread out. Okay, like we saw with the graphs that I drew by hand on Monday's class meeting. Okay, so any questions about our simulation or anything like that before we just kind of go through the other three circuits that we can make with a series RLC circuit? Kyle, what's up?
If, where would you put that on this something?
So you would do you'd have your antenna, the signal of the antenna is going to be fed into the filter. Actually, you're probably going to wind up having an amplifier after the antenna and before the filter, and then another amplifier, a power amplifier after the filter, to drive your speakers. Any other yes?
So changing the resistor value would, the only difference that I would make would change the inductor and capacitor value.
So if we change the resistor value for this thing, so we have a very specific corner frequency in mind because we have a fixed value of L and C. So if we made our resistor value larger, let's go back to our relationships and see what would happen, right? So our bandwidth is defined as R over L. So if we make R larger, we should see that that peak spreads out. So let's just throw in, instead of having a 1K resistor, let's look at what happens with a 10K resistor. I would expect this to get 10 times as wide. Rerun our simulation. And yeah, it just broadened everything out.
If we change that, would we also change the capacitor and inductor and
If we wanted to maintain that 200 kilohertz bandwidth, we would wind up having to change. So if we increase the size of our resistor by a factor of 10, we would need to increase the size of our inductor by a factor of 10. And I think, let's see. Our capacitor. I'm not sure on the capacitor. Let's see what happens. That's definitely not right. Capacitor might need to get smaller by a factor of 10. Yep. So inductor increased in size by a factor of 10, capacitor decreased in size by a factor of 10, and we're back to our original graph. Yeah.
Do they be in pair or like what if one is a constant resistor?
I'm sorry, what was that?
Do inductor and capacitor is being there, or, I mean, what if one is a closer resistance?
So let me make sure I understand what you're asking. I'm going to go back to page 10 here for kind of scratch work where this isn't particularly specific to this thing. So if we had a filter network, and I may be misunderstanding you. So right now, we have everything in series, right? So are you asking what would happen if we put something else in parallel with the, okay, so let me scroll back up here. So you're saying, oh my goodness. What would happen if we put a resistor right here? Well, so that's just going to change this transfer function, right? So if this was, say, an R1 and an R2 down here, we would effectively have R1 and then this one be R1 plus R2, and we'd need to redo all of that math. So we're only going to get a bandpass filter behavior where our output voltage reaches our input voltage if we're taking the voltage drop across the total resistance of the circuit, okay? If we added another resistor in there, then we essentially have a little bit of voltage division so that our output isn't going to actually climb up to 0 dB. So our peak value might be -5 dB, -6 dB, or something like that if the resistor is fairly small. If so let me think about this. If the resistors, if you had two resistors in series of the same value, then the peak value should drop down to about -3 dB, because that's corresponding to a factor of 1/2. Okay, or actually might be -6 dB for a factor of 1/2. If the resistor that you're not taking the voltage drop over, that one that you just inserted there, was significantly larger, then that's going to make your maximum value of your transfer function lower and lower and lower on the dB scale. So it's starting at 0 dB with a resistor value of R right here as 0. And then as this R gets larger and larger and larger, your peak is going to go down and down and down. So you're making your filter attenuate more at the resonant frequency. Any other questions about, yes?
So how would you change the station? Like practically, how would that look like?
Fantastic question. Okay. So in most old school radio applications, that is done by having a variable capacitor. Okay. So essentially, if your capacitor's value can change, that allows you to change the resonant or center frequency of the circuit. Okay. So that potentially begs the question of how do you implement a variable capacitor? And there are a couple of different ways that you can do it, okay? So in some electronic circuits, you use what's called a varactor diode. So that is literally just a diode that is meant to be reverse biased. And depending on the voltage drop across that particular diode, it's going to cause the capacitance to change. So it's going to have its largest capacitance when it is unbiased. And then as you increase the reverse bias voltage across that capacitor, it is going to, the capacitor is going to get, capacitance is going to get smaller and smaller and smaller. You learn more about that in Electronic Circuits 1 in the winter, but Dr. Z might talk about it some in your solid state class as well. Realistically, the capacitive tuning range on a varactor diode is really only in the ballpark of about 10 to 15%. before the capacitance winds up getting so small that it doesn't really have much of an impact. A different way to do it is to have a capacitance whose value changes due to mechanical change in the system, okay? So I'm gonna have to use my hands for this, so Zoom isn't gonna pick it up or whatever. But there are physical capacitors that are essentially parallel plate capacitors, and they start with a position where there are several plates and they are overlapped like this. And then as you turn a knob, it mechanically rotates these fingers out of the plane so that the area of overlap between the fingers changes. So right here, we have maximum overlap. When we're 90 degrees out of phase, we have minimum overlap. And so because that area of overlap is changing, the capacitance value is also changing. So that's how like old school physical variable capacitors work. I used to have one in my research space at the IFM, but I don't know what the hell happened to it. But it was an old Russian variable capacitor that I used for an impedance matching network. So I would just change out various inductors to get close to the frequency that I needed, and then just literally tune that capacitor to whatever impedance that I was looking for. For what it's worth, you can have more complicated circuits that do a similar thing. So you can make your center frequency wind up changing due to either a changing inductance, which that's a little bit harder. Finding a variable inductor is a harder thing to do. But there are some circuits that can do it by changing the resistance value, but it's not going to be a simple RLC circuit like this. Are you aware of what a wah-wah pedal is for an electric guitar? So a wah pedal is literally a bandpass filter where the center frequency moves depending on what the position of your foot is. And that thing on your, where you press down on it, so it actually has this geared thing that turns a gear on a potentiometer, which is just a variable resistor. And as you sweep your foot, you know, down to up or up to down, that's literally changing the center frequency of that filter. And that's why it makes that wah-wah noise. Anything else about this bandpass filter? Okay, so let's talk about the other types of filters then real quick, okay? So this is going to be similar to what we did at the end of our last class meeting where I literally just draw the picture of it and then give you the relationships because the derivation is effectively incredibly similar. So I don't want to waste you guys' time with that. So let's start with a low pass filter, okay? So this will be second order low pass filter, okay? So as I mentioned before, for a low pass filter, we're going to take the voltage drop across just the capacitor, okay? So for our circuit diagram, it's going to look something like this. So here's Vn, here's R, J omega L. Here's 1 over J omega C. And our output voltage is just the voltage drop across our capacitor. So we could find that our transfer function for this particular circuit with a little bit of algebraic manipulation comes out to be omega squared LC over omega squared LC minus 1 minus J omega RC. Splitting that up into its real and imaginary parts would give us omega squared LC times omega squared LC minus 1 over omega squared LC minus 1 sorry, just making sure I didn't make a mistake there. squared plus omega RC quantity squared plus J times omega squared LC times omega RC all over that same denominator. Omega squared LC minus 1 plus omega RC quantity squared. Our magnitude response would look like omega squared LC divided by the square root of omega squared LC minus 1 plus omega RC squared. Sorry, both of these should have been squared. Our cutoff frequency, let me back up here a little bit. So I'm just giving you a warning. This is a gross thing. So we're going to have the square root of R squared times C quantity squared minus 4 R squared LC plus 8 L squared all over 2 L squared C quantity squared. That ends that square root plus 0.5 R squared C minus L all over L squared C. Close that bracket, square root that whole thing. And our phase response, theta as a function of j omega, is going to come out to be the inverse tangent of omega RC over omega squared LC minus 1. Okay. Oh, I'm sorry. Dang it. So I said that this was a low pass filter, which it totally is. I accidentally drew the circuit diagram and all of the notes and all of these relationships were for a high pass filter. So let me fix that. I apologize for that mistake there. So that should be high pass filter, which means this should be an inductance. And that should be the capacitance. My mistake. I apologize for that. Let me just double check these relationships. That seems legit. That seems legit. That seems fine. Okay, sorry for that. The low pass filter correctly this time. Let me make sure I'm on the right page. Damn it, now I'm writing HPF instead of LPF. Goodness. So this is the one where we're actually taking the voltage drop across our capacitor. Again, my apologies. So here's VN R J omega L 1 over J omega C. Here's V out. And let's see, so our transfer function comes out looking like 1 over 1 minus omega squared LC plus j omega RC. Breaking that into its real and imaginary parts, we have 1 minus omega squared LC over 1 minus omega squared LC squared plus omega RC squared minus j omega RC over 1 minus omega squared LC squared plus omega RC squared. Magnitude response comes out to be 1 over the square root of 1 minus omega squared LC squared plus omega RC squared. For what it's worth, the corner frequency omega C is just same as second order high pass filter, literally the exact same relationship. And our phase response, theta as a function of j omega, is negative the inverse tangent of omega RC over 1 minus omega squared LC. Let me draw that bracket better. And I think the only one that we have left to do is the band stop filter. We've got a minute or two here. So thus far, we have taken the voltage drop across the resistor is how we got a band pass filter. Voltage drop across the capacitor is how we got a low pass filter. Voltage drop across the inductor is how we got a high pass filter. So what do you guys think we're going to take the voltage drop over to get a band stop filter? So a band stop filter means that we're going to pass low frequency signals and pass high frequency signals and attenuate middle frequency signals. Exactly right. Exactly right. So because we're getting the opposite response, or we want the opposite response of when we took the voltage drop across the resistor, we have to take the voltage drop across everything that isn't the resistor. Exactly right. And a way to think about that, just for what it's worth, let me draw it out here. So second order band stop filter. So this is our circuit. Here's Vn, here's R, and then we're going to have j omega L in series with 1 over j omega C. Right, like so. So effectively, at very low frequencies, that inductor in series with a capacitor looks like an open circuit, which means there's no current flowing through that path and there's no current flowing anywhere because we have our output terminals open circuited. So no current flowing through that resistor R means there's no voltage drop across that resistor R, and so V out is exactly equal to Vn. At very high frequencies, that shunt branch with those two elements in series also looks like an open circuit, so that's why it passes everything at high frequencies as well. It's only when the reactance of the inductor and the reactance of the capacitor start to cancel each other out that we see that our signal is actually attenuated, because then we're taking the voltage drop across what is effectively a short circuit. Okay. So for this guy, our transfer function is going to be 1 minus omega squared LC over 1 minus omega squared LC plus j omega RC. breaking that into the real and imaginary parts, we'll have 1 minus omega squared LC squared over 1 minus omega squared LC squared plus omega RC squared minus J omega RC times 1 minus omega squared LC divided by 1 minus omega squared LC squared plus omega RC squared, like so. Our magnitude response H of J omega is 1 minus omega squared LC divided by the square root of 1 minus omega squared LC squared plus omega RC squared. For what it's worth, omega naught, omega low, and omega high is going to be same as our band pass filter that we talked about at the very beginning. Exact same relationships, okay? Same thing for bandwidth for what it's worth, obviously. And so our phase response, theta as a function of J omega, is the inverse tangent of, I think that should be negative omega RC over 1 minus omega squared LC. Yes. Okay, so we technically have 4 minutes left of class. I know I rushed through that. That was kind of intentional because I want to talk to you guys about your test on Friday. So your exam on Friday is going to be overwhelmingly related to AC circuit analysis, okay? The only thing that I might ask you to do on your exam related to the filter material that we've covered over these last 2 days is to just give me, I might give you a simple series combination of circuit elements. And I want you to be able to do like this style of transfer function, okay? You don't need to break it down into its real and imaginary parts. It's literally just use the voltage division relationship and then simplify it if necessary. That's it. It will be a 5-point question, and you should realistically just consider it a bonus because you haven't had any homework or anything like that related to it, but it is straight up. Can you apply voltage division to a simple series network containing impedances and then possibly simplify things a little bit if needed? That's it. Yes.
What are you going to simplify things about how we went through in class today, or like what do you?
So like for this very first example up here, I multiplied through by a factor of J omega C over J omega C to get rid of my fractions inside of my fractions. That's the level of simplification that I'm looking for. Nothing past that. If you want to break it into the real and imaginary parts, good on you. You're not going to get any extra points for that. Literally, that problem should take you 2 minutes tops to math it out. End of story. Okay. You're not going to have a homework assignment based on filters at all. You're just going to have the design project where you have 2 different prompts related to what we covered today. I think I give you a band pass filter and a band stop filter because, as you may have noticed, the math behind what's going on in the low pass filter and the high pass filter for your cutoff frequencies is super annoying, and I don't want to make you suffer through a bunch of stuff to figure out how to get a specific corner frequency. Okay. Yes. You will get to create your own equation sheet for this upcoming exam. You can put anything you want on it, 1 page, front and back. It will be collected from you when you finish your test. Okay. So 1 page, handwritten, front and back. Any other questions about the exam? All right, so realistically, you should treat this exam like a much shorter version of exam 3 from circuits 1. Because that's the material that I'm testing you on. Anything having to deal with multi-frequency circuit analysis is going to be on the take-home test because it takes too damn long to do it for the in-class portion. So this test on Friday is straight up exam 3 from circuits 1, but shorter. Okay. All right, I won't see you guys on Friday. I legit don't know who I'm having proctor the test yet. That is on my list of stuff to figure out today. So I'll see you on Monday for sure.